Okay, in this video we're going to do first in a few videos about algorithms and specifically we'll be looking at selection sort, and we'll start by looking at this link here which I already have open. But before that I want to say just some sort of generic things about algorithms. So you want to have a one sentence description of an algorithm, and an algorithm is in one short phrase a set of instructions to solve a problem. Note, problem should be extremely well specified, and so should the set of instructions. Okay, we're going to look at an example here with sorting numbers. Note, computer science is really about programming and algorithms. So that's computer science. If you're just going to say two words, programming is what are the rules about how to tell the computer what to do. That's what we've been doing. About data files, syntax of JavaScript and HTML, and then algorithms is what are the ways to organize the data and solving the problem. So there are better and worse ways, and we'll see examples of that. Okay, we're going to start with an example. And the example is going to be sorting. So we're given a list of numbers. The goal is to produce a sorted list. Normally we use n as the number of numbers. Just in case we need to talk about how many numbers there are, we use little n for that. Now let's go over here. This is a link from Tutorials Point about selection sort. Selection sort is a specific way to solve the problem. So we would have here an instance of the problem, and how many numbers do we have? 8. So here we would have n equals 8. This is just some list of numbers, and we want to produce a sorted list with the smallest first. Okay, if we want the smallest first, which one would it be? So that would be 10. And then what would be next? 14. And what would be next? 19. And then 27, 33, 35, 42, 44. And they're going to explain how selection sort actually does that and produces this final list. But what you want to think about is how would you write a program to do this? When you look at the problem, you just look and you see 10 is the smallest, and you don't really probably think about it. But for the computer, so when we're writing a computer program, we have if statements, while loops. Any given time when the program is running, it's only looking at one variable. So any of our programs that we would look at, happens to be a program that does selection sort. But if we're running the program, it's in here somewhere. Maybe it's doing this if test right here. And while it's doing this if test, it can only look at one number at a time. So there's a number, and this would be some number as well. We'll look at that code in a minute. So what we want to think about is how would we solve this problem if we can only look at one number at a time? So what we might think of is we might be allowed to look at the first number, and then we don't know at the moment what the rest of them are. We just know the first one's a 14. And then we might look at, so if I want to cover this up, so we might look at the second number, and we wouldn't know what the rest of them are. And then we could look at the next number after the 33, but then we might forget what the 33 is. So if we can only look at one number at a time, what is a way to solve this problem? And there's a lot of ways that are pretty easy to understand. And if you pause the video and make up some way that you would solve the problem, one of the ways, probably somebody in the class would come up with selection sort, and somebody else would come up with some other sorting algorithms. So I'll tell you the basic idea for selection sort, and then we'll see how we think it should go. So selection sort. So the basic idea is scan through the list to find the smallest number. Use a for loop and put it at the beginning. Then scan through the rest of the list to find the second smallest and put it second. Repeat. Okay, so the basic idea here is, put this in italics, we want to look through, we can look at one number at a time, and we want to find the smallest. So what we could think of is, let's move this over here, and I'll move this over here. If we were writing a program for this, we might have some variable called smallest so far, and we would be able to look at one element at a time. So at the beginning, the first thing I've seen is a 14. And maybe I want to keep track of the index. So which position in the list was that? That's a 0 because we have position 0, 1, 2, 3, 4, 5, 6. Okay, so before we do anything else, we look at the first one, we see that there's a 14. If we're doing a loop, we can have the index go 0 up. So we would look at the next one, and we would say, okay, is that smaller than the one that I've seen before? I'll make it so that I can only see the 33 now. All right, so that's not smaller than the 14. I can remember the 14. Okay, is the 27 smaller? No. I can remember where I am in the array. Now I see the 10. Okay, that's smaller than 14, so I should put a 10 there, and that's at index 3. If I'm inside of a for loop, I would have a counter. All right, we would go to the next one. 35, not smaller than 10. 19, not smaller than 10. 42. And 44, and we would be to the end of the loop with 10 is the smallest. So what we would want to do is take 10 out and put it at the beginning. There's different ways to do this. The easiest way is just to swap it with 14. So we just put 10 here at the beginning and put 14 over here. That only requires changing these two items. Rather than, if you're doing this on paper, you might cross out the 10 and put it over here. In the computer, that would be really like shifting the whole list. The easiest thing in the computer is just take the 10, put it here, take the 14 over here. And that's what they're going to do, and I'll update our little description. Put it at the beginning, so this would be swap with first item. And they're going to have a nice little picture. So here, they've colored this blue to say that's the spot where we want the smallest to be, and this is red to say that actually is the smallest. And then they do the swap. Now 10 is over here, 14 went over here. Green means that that part is good. We know that 10 is supposed to be at the beginning. Okay, so now what would the next step be? You pause and then say what you think the next step would be. The next step in selection sort is, we already know that's sorted. We can just look at the rest of the list and we want to find the smallest there. And again, we would have we would be starting here with the first thing in the rest of the list, which is the 33, and in the whole list that's at index 1, and that's the smallest that we've seen so far before we scan through the rest of the list. We move over, 27 is smaller, so we save that. That's at index 2. We move over, 14 is smaller than 27. That's at index 3. We move over, let's just, as we go all the way through, we keep looking at the next one, and none of them is smaller than 14. So it should be that 14 should go here. And there we see, when we go to the next stage, this is where we want the second smallest to go. This actually is the second smallest, so they should switch. And there they have the 14 down here and the 33 over here. Alright, what should happen next? We know that these two are the smallest two, and they're in order right there. Now we want to find the smallest out of this group. We just do the same thing again. We're going to end up finding 19, but in order to find out that it's the smallest, we have to look at each one of these again. So we would start over with our picture here. We'd have 27 is the smallest out of the rest of the list. It's at index 2, and we would go through, and eventually we would have that 19 is the smallest out of the rest of the list at index 5, I guess. Alright, and then we would know that 19 needs to switch with 27. There's the 19 right there. And then they switch 19 down here, 27 goes over there. And this would just keeps getting repeated. The smallest out of this part of the list is now 27. It's going to get switched with 33. Now the smallest out of this whole part is 33. That's going to get switched with 35. The next part of the list, they just skipped to the end result here. Actually, the rest of it's sorted. But if we were looking for the smallest out of the rest, it would be 35. You could say that it switches with itself. Same thing would happen with 42 and 44. So this would be the finished sorted list. Alright, so what you could do right now, pause for a second, start over, and say to yourself, what is the algorithm? And then you can go back over and check and see my description here. What you could do is try to think about what would the code for this look like. And we're going to look at the code now. So this is it's in the class directory. I have a directory called algorithms, and there's a file sorting. And I have this example here ready to copy and paste and run. If we run it, so node sorting.js, and there's the numbers that we started with over here. 14, 33, 27, and so on. And it says this was the input list, and then there's the sorted list. Sorted list. Okay, and this is the code. So we'll just sort of walk through the code here. Here we're checking arguments. That's just like normal. There should be at least one number. So the length of the argument should be at least 2 if we're going to have node, the name of the file, and then a number. Selection sort is a function here. It starts running past that. Here we have process.argv.slice. So this is something that I'm not going to ask you on a test, but this takes the part of process.argv starting at index 2. So that would be just the numbers. This slice works like a slice in strings. So it starts in index 2 and goes to the end. List will just be the numbers. This thing here applies parse float to each item in list. So this argv is strings. Right, argv gives strings. If I want to apply the same function parse float to all of them, this is a way to do it. So now list is an array of my numbers. Okay, and then here we just print it. There's selection sort, and there is when it's done. So we're going to go in and look at selection sort. Up at selection sort, list is an array of numbers, and it's supposed to become sorted. Okay, let's look at, so here's some code. There's a thing called smallest index. Let's think about I. Here's a loop, I equals 0, I up to less than the length. Let's do this. We'll keep track of what happens here if we have the list is this, and then the index of each of these 0, 1, 2, 3, 4, 5, 6, 7. Okay, there's 8 numbers. All right, we get inside of this function here. We'll start out with I is 0. And what this loop is supposed to do here, when I is 0, it's going to find the smallest. So it's going to do this part where it finds the smallest and swaps it, and we'll see how that works. But to begin with, we have I is 0, and then we have smallest index is 0. And then we have j is I plus 1, so what's that going to be? 1. And then we go inside of this this loop here. So I'd be down on this line right here, list bracket j, so that's the 33. Is that smaller than list bracket smallest index is 0. So what I'm thinking here is my smallest is my 14, because I'm looking at list bracket 0. Alright, so is this 33 less than the 14? No. So this doesn't happen. We go up in the loop, we increase j. Is j less than the length of the list? Yes. Then we're going to look at the next item. List bracket j is going to now be this 27. Is 27 less than list bracket 0? No. It's comparing the 27 and the 14. J goes up by 1. Now we're at list bracket 3, which is the 10. 10 is less than 14, so we do this. Smallest index becomes 3. I don't have a variable called smallest here. I don't need one because I have the index, but if I had one, it would be 10. And then j would go on to be 4, 5, 6, 7. Each time, all of those are going to be not less than 10. When j gets up to be 7, we go up, we do j++, and then we say, is 8 less than the length of the list? It's not less. The length of the list is 8, so it's not less. That loop would be done. So I need to go down and look, is there anything else down here? So then I have this code here. We have item I is now list bracket I, okay? Item I is list bracket I, that's this position here. So I is the position where we're making the switch. I'm at the beginning, so I'm going to switch into the beginning. So item I is 14. Then we're going to take list bracket I, that's this 14, and we'll put in there list bracket smallest index, that's the 10. So I put the 10 in there. That's what this line does. List bracket smallest index, that's my 10. Okay, now list bracket smallest index, that's the spot where the 10 is. That gets item I. So that's doing my swap. Alright, then the for loop with the I is down to the end. We go I plus 1. And at this point, we're right here in this picture. So my list here looks like this. My I is at 1 to say that's where I'm going to be working. That would be the blue. I want to put the next smallest thing here. And then I go down to this smallest index equals I. So that would be now 1. And the 33 is the value that's there. When I start my J loop, what is J going to be equal to? Just I plus 1, which is 2. So I'm looking at this 33, and the first thing I'm going to check is 27 less than 33. It is. So then this statement here will happen. Smallest index gets the value J, which is 2, and the value that's there is 27. Then we go, J is 3. Is 14 less than 27? So list bracket 3 is 14, list bracket 2 is 27. 14 is less than 27. So we put the value of J into smallest index. And then J goes through the rest of these values. None of them is going to be less than 14. In the end, J gets the value. What is the final value of J? After this loop here finishes, what was the value of J? It's 8. Okay, because it gets past, so it gets to the value where this condition is false, and that's 8. Alright, we get down here, list, item I is list bracket I is 1, we're looking at the 33 here, so item I is 33. Then we have list bracket 1, that's the 33 here, that's going to get the item we had here of the smallest, so that's going to be 14. And then where the 14 was, this puts the 33, the item I. Then we go up, we get the next value of I. I will go up to 2. And we're going to do this whole business again, and smallest index goes to 2. So we'll be working on this right here. We want to put the next smallest right there, which is going to end up being the 19. But we could go through all the values of J to see that happen. Maybe we'll go through just one more time. Okay, so smallest index is 2. What does the value of J get set to? This happens here. J equals I plus 1, which is 3. And let's see, at index 2 right now we have a 27. So be checking this would be 33, and this is 27. It's not smaller, so we don't do anything. J goes up by 1. Now we're looking at this right here is 35. This right here is 27. It's not smaller, so just J goes up by 1. Now we have 19 is smaller than 27, so now we're going to save that value of J, and that's the smallest that we have in that part of the list. And that would be it. Neither one of these is smaller than 19. J ends up going all the way up to, it'll be 8 after the loop. And then we have item I is list bracket I. List bracket I is 27. then list bracket I gets the smallest, and wherever the smallest was gets this 27. And that would be it up to the first 3 items, and then I goes up to 3. So if you wanted to, you could pause this and keep going through yourself. I goes up by 1, you have a new smallest index, you go through all the values of j. When you get to the end, you should have wherever the next smallest was. For the next one, it should be j is 5. Smallest index will be 5 at the end. That will get swapped. This does the swap right here. And it just keeps going like that. Okay, if we wanted to, we could print here what the list looks like each time. So each time through, we should see, and then we would see it starts off like this, and then it would be changing each time. So we have, this is the original list, and then the 10 gets put in, and then the 14 gets to be second, and the 19, and so on. And eventually it's sorted. Okay, so now would be a good time to take a pause. You want to make sure you understand the idea of the algorithm and what each line of the code is doing. And I will even take a pause as well for a second. All right, hopefully you took a minute to try and digest this. Let's see, on the notes for the lecture, I'll tell you what you're supposed to know. Here we are. Good quiz questions. Given a list of numbers, what does the list look like for each iteration of selection sort? So you could go to run my sorting program and before you run it, say what the list would look like each time. So the first time here, 3 would go at the beginning, 3 would get switched with 23. Next thing that happens, there's another 3, so the 3 would get switched with 78. So you could print out, you could write down on a piece of paper what should the list look like at each step, and then you can run it and see and make sure that you got the right answer. That would be something that I could ask you on a quiz or exam, including the oral part of the exam when we talk on the phone. So you want to be able to do that. All right. Other information. So what's the point? Sorting is a thing that has to happen. Having information in sorted order is much more useful, and it's easier to find information. It'll be important to note what is the running time. So the running time is how many basic steps or how many lines of code. And what I mean by that, if we look over here and we just put our cursor on whatever line's happening each time, first we come in, we have I equals 0, we're on this line. And then we go to this line, and then we go to this line. We're in this for loop, we do this if test, go back to the for loop, do the if test with a new value of j, j++, so you're sort of going back like this. Eventually you get down here, we do these 3 lines, we do a swap, but then it goes back up to this line. So every time we're on a new line of code, we would count that as a basic step. And how many basic steps are there in this? So what we want is a formula. We want a formula for how many basic steps an algorithm or a program takes, depending on the size of its input. For sorting, how many numbers? So for sorting, given a list with n numbers, how many basic steps? So for selection sort, we can come up with a formula relatively easily, and it's actually easier to look at it here and then come back and verify the code. All right, if we're going to find out that 10 is the smallest, how many of these numbers did we have to look at? We have to look at them all. So the answer is, to find the smallest, before you do anything, we have to look at all of these numbers. So first we think 14 is the smallest, still smaller than this, still smaller than this. Oh wait, 10 is smaller. Okay, now we need to check it against this one, this one, this one, this one. Basically, we have to look at the whole list. So the number of basic steps there is n steps to find smallest. All right, that would be finding the 10. Now what about finding the next smallest? So we want to go through this list and see what's the smallest. First we think it's 33. Okay, that's a number. 27 is smaller. Okay, let's remember that one. Oh, 14 is smaller than 27. Let's remember that one. But then we need to check it against this one, and this one, and this one, and this one. If we started with n numbers, how many did we look at here to find the second smallest? The answer is n minus 1. Okay, then we would have the two smallest. What about the next one? Well, we have to look through every number that still we haven't sorted. So this would be now n minus 2. And so on, all the way down to one step, when we only have one thing left unsorted. That doesn't, you could say we can skip that, but we can leave it there. So the total then would be something like n plus n minus 1 plus n minus 2 plus dot 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 down to plus 3 plus 2 plus 1. It goes down by 1 each time. There's a formula for this, something that you probably should just remember, especially if you're going to do computer science. If you're adding up 1, 2, 3, and so on up to n, the formula is n times n plus 1 over 2. Okay? And if I want to say the most important thing to remember here is we call that big O of n squared. So if you multiply that out, that's actually n squared over 2 plus n over 2, right? If you just multiply it out. The most important thing that's happening there is n squared. When n is a million or a billion or whatever, large lists of numbers, the n squared is more important than this n over 2. It's more important than dividing by 2. That's called big O of n squared. And they say that here, big O of n squared. So I'll make a note here, big O. So big O basically takes the most important term in an expression for running time. and gets rid of the constant that is multiplied. So here, this half, multiplying by a half, most important term, largest. So multiplying by a half doesn't really matter there. The 2 in the exponent does matter, right? We don't get rid of the 2 in the exponent, we get rid of the half there to say the most important thing that's happening is n squared. So an example is n squared over 2 plus n over 2 is big O of n squared. Right, another, we could do another example. Say we have n to the third, let's say 100 times n to the third, plus n to the fourth over 10 minus n cubed. All right, so out of all of that, what's the most important? Or let's say this is an n squared. Out of all of that, n to the fourth is the part that matters the most. When n gets big, this n to the fourth matters more than this 100n cubed, and it matters more than this n squared because we have a higher power of n. So we would say that this is big O of n to the fourth. That as n gets bigger, what's really happening here is n to the fourth. Note, for now, you just have to memorize that selection sort is big O of n squared. That's it. Okay, so the key takeaways here, what is an algorithm? Set of instructions to solve a problem, a specific set of instructions that a computer or a person could follow without thinking. Problems should be well specified, so should the instructions. So computer or person can follow the instructions without having to make any decisions, right? So if you don't specify the instructions well enough, then the person may have to decide on what to do. You don't want them to decide what to do. You have a program. So here I have a program that is definitely a well-specified set of instructions. Okay, so an algorithm is a way to solve a problem. Set of instructions to solve a problem, a way to solve a problem. Selection sort is an example of an algorithm, a way to solve the sorting problem. Okay, so that's what an algorithm is. Computer science is really about programming and algorithms. All right, so that's important. There's sorting. So selection sort is n squared. Other order n squared sorting algorithms. Insertion sort, bubble sort, shell sort. So all of the ways that you would think to do sorting are normally going to end up being n squared. But there are sorting algorithms that are order n times log n. And have we looked at what, let's see. Yeah, I think we've looked at logarithms before. So here we have n squared is n times n. This is n times log n. Log is really small. So log of a million, if you have a base 2, so the base doesn't really matter here, but let's see. If we have a base 2, if n is a million, then log base 2 of n is like 20. So instead of having n times, so n squared would be a million squared, this would be 1,000,000 times 20. So that's much, much smaller. So this is important. Not that we know what those other ways to do sorting are, but if we just do the first thing that comes into our head for how to solve the sorting problem, it's going to be n squared. If we study computer science and learn a better way, more efficient way, then we increase the running time. So let's say for n equals, let's say 10 to the 9th. That's 1 billion, right? Like all people on Earth, or all people in China. So for n to the 10 to the 9th, then that is, so the improvement in the running time would be, instead of an 10 to the 9th, we'd have log 2 of 10 to the 9th, which is like 30. And what is 10 to the 9th over 30? Does Google understand that? 33 million. Let's just call it 30 million. So that is something like 30 million times faster. It's actually not exactly going to be 30 million, it would be more like 10 million, but okay. So that is why computer science is more than just programming, it's also algorithms. It matters trying to figure out the best way to solve a problem. All right, so in the next video in the algorithms sequence of videos, we'll do another problem, another algorithm, binary search.